And as part of Bridgework, we wanted to bring some of those students out of their different departments to talk to you and also to talk to one another. Environmental change and challenge is not just one department's province. It is relevant to the research and teaching and learning that we do across all of the divisions and departments, academic and otherwise, at this institution and at every institution. And we're delighted to have a real mix of disciplines here today. We have geology, we have engineering. Dr. Hanrahan said we need engineers involved in this. We have theology and ministry. We have meteorology and environmental science and chemistry. So how about that? And we have 6 really wonderful students to talk to you today. They're going to introduce themselves.
So as Dr. Lynn mentioned, my name is Dylan Antonides. I'm a senior mechanical engineering major here at Valparaiso University. And my interest in sustainability particularly revolves around kind of how different disciplines can work together to achieve sustainability, and then also sustainability in the automotive industry. But my presentation, as you can see in your program, is on solar energy. To my knowledge, the oldest law regarding solar energy was penned in the 6th century AD in ancient Mediterranean. Following a fuel shortage in the 5th century, architects of the region began to use the sun as a passive heating element for their buildings. Romans, in particular, began constructing domed, south-facing rooms like the one you see in this photo. They were closed in by windows of glass or mica. In the winter, these heliocamini, or sun furnaces as they were known, were kept warm purely by energy from the sun. In the Codex Justinianus, the Byzantine Emperor Justinian I issued this decree: if any object is so placed as to take away the sunshine from a heliocaminus, it must be affirmed that this object creates a shadow in a place where sunshine is an absolute necessity. Thus, it is in violation of the heliocaminus' right to the sun. Now, let's fast forward to today. We know that the sun is an almost inexhaustible resource. More solar energy reaches the surface of the Earth in 1 hour than all of humanity uses over the course of an entire year. It is an accessible, increasingly inexpensive source of energy, yet only provided less than 2% of the United States' total energy usage last year. If our total energy consumption was a typical bag of Skittles, 1 Skittle would have been produced by solar energy. Why is this? Largely, it's a storage problem. We cannot collect solar energy when the sun isn't shining. Batteries can help solve this problem by letting us store the energy overnight, or at least maybe up to a week. But what can we possibly do for these interminable Northwest Indiana winters, where we probably won't see the sun for at least 6 months? Research suggests that with existing distribution and storage technology, we can provide at most 30% of our nation's energy needs using solar energy. Only 30%. So, as you can see, long-term energy storage is a major hurdle for solar energy. And as some of you have probably surmised by this point, this is where Valpo comes in. Our solar energy research facility, which we fondly like to call the SERF, studies solar chemistry. Specifically, I've been studying a process that has the potential to be the most efficient, renewable method of producing hydrogen gas in the world. Wait, hydrogen gas? Yes, hydrogen is an extremely high-energy, stable chemical that can be stored carefully for decades. The only waste product associated with using hydrogen fuel is water, whether you're burning it to produce heat or using it in a fuel cell to produce electricity. Our hydrogen process is visualized here. Let me explain. We use cobalt oxide, represented by the green loop in the center, as a go-between to break hydrogen production into 2 steps. Forget this graphic for a second and think of cobalt oxide as a sponge, but not a sponge for water. Rather, it is a sponge that absorbs oxygen atoms. In the first step of the process, we dry out the sponge in a reactor that's heated with concentrated solar energy spinning and shaking much like a clothes dryer. The dry sponge now has lost all of the oxygen that we can push out of it. The only inputs to this step are the chemical sponge coming from the bottom of the slide and solar energy from the left. In the second step, the dried out oxygen sponge is mixed with water. When a relatively small voltage is applied to the mixture, the sponge robs oxygen from the water, becoming saturated again, and leaving behind only our hydrogen gas that we can collect and store. Even better, once the sponge has performed its task of absorbing the oxygen, it can immediately be fed back into the solar step of the cycle and dried out again. In this cycle, the sponge chemical is constantly recycled and reused, so the only external inputs to the system are water and solar energy, and the only output is hydrogen fuel. There are teams of students and faculty at Valparaiso University dedicated to tackling problems inherent in both of these steps. I spend the vast majority of my time with the solar team, which is faced with the task of optimizing the reactor. As simple as it sounds, drying out the sponge is a lot more simple than just wringing out my own dish rag. It involves using solar energy to heat up the chemical to just under 2,000 degrees Fahrenheit, maintain it at that temperature just long enough to drive out all the oxygen we can, and then cool it as quickly as possible to prevent our chemicals from just reabsorbing the oxygen we drove away. Think back to your dish rag, and imagine trying to wring it out while it's underwater. You have to move pretty quickly to get it out of the water without getting wet again. And this is analogous to what we're trying to do in the solar reactor with our oxygen sponge. However, we've had a couple years to work on this, and we've developed a system that's actually very effective. We can remove over 85% of the available oxygen from the sponge, which is better than any other institution in the world using a solar process. This two-step hydrogen production cycle, though it has the potential to be revolutionary, is far from being industrially viable at the moment. Looking back on our initial goal, which is to develop technically and socially viable long-term solar energy storage that does not exacerbate climate challenges, we're considering now how this process can be implemented on a larger scale. In the next iteration of the solar reactor, which I helped build this semester, we intend to give future research teams the ability to do just that, to begin scaling up production to a level that more closely reflects what would be necessary in an initial industrial application. Every measured pace brings us closer to renewable, long-term energy storage, decreased greenhouse gas emissions, and a brighter outlook for our planet and our children.